Hi everybody, buongiorno, buon pomeriggio. Thank you for the invitation. That's a pity that I couldn't make it, but I really appreciate the possibility to give this presentation online. So what I want to discuss today is a kind of progress and the perspective that we are seeing concerning the use of van der Waals heterostructure to elaborate spintronic application. And first of all, I like to mention that part of my presentation is inspired by a very recent review articles that we are publishing in Nature Nanotechnology with Sierra, Fabian, Kawakami, and Valenzuela. So at the time of the workshop, Transient Magnetism, this paper will have been fully published. So why are we interested in graphene and van der Waals heterostructure? Everything started almost 10 years ago when the graphene flagship project was selected by European Commission and launched. In its mission, it was clear that these two-dimensional materials could present very interesting perspective for spintronics. So that was one of the direction of investigation. And what made graphene so attractive at the time, there was this materials just based on carbon, and sp2 configuration was anticipated to be an extremely good conductor of spin information, given its low spin orbit interaction and very large mobility. Many years later now, we have the conviction that indeed these materials offers unique perspective for transferring spin information over unprecedented scale. And this is a result published by IMEC and ICN2, in which they show that at room temperature, you can achieve very long spin diffusion lengths or spin lifetime and spin lifetime in a scalable graphene, the graphene that you can grow with catalytic vapor deposition, CVD, so which make the system very useful for application because it's integrable. Also, let me say that it's not very necessary to achieve a huge mobility to reach those numbers that are enough for designing active spin device. Essentially because, as we could show theoretically, the spin diffusion lengths does not really depend on the sources of scattering or the strength of scattering, because in these polycrystalline morphologies, it turns out that it is just related to the spin orbit coupling strength that is induced by the substrate on which graphene is deposited. And CVD graphene is one of the most important materials now for wealth application beyond spintronic, as you can see here in this plot several illustration of groups and institutions that are working with CVD from graphene in real application. What is also very promising is the fact that the European Commission, together with Graphene Flagship, have launched the so-called experimental pipeline. And this is really important because you really need to have this large volume production of functional electronic devices based on these two-dimensional materials, but you need the proper infrastructure to develop this kind of architectures and devices. So there is now an important effort that has been initiated and hopefully will be maintained in the next 10 years, because there is still a long way to go in order to come to very efficient commercial products but a foundry is necessary to move towards this objective. And particularly now, thanks to the large-scale graphene, you can engineer very complex architecture. You can deposit a lot of different type of contacts, and you can probe the spin information propagation over very long distance through very different type of interconnected devices. So the graphene flagship also put in places a European task force to explore the full capability of these materials for spintronic application. And since then, we've been very active in demonstrating the potential of graphene and two-dimensional material and van der Waals heterostructure for concrete spintronic application. We elaborate a roadmap in 2015 that we have followed quite regularly. And let's say one of the major aspects and the most interesting property of graphene is that not only it can transfer information over unprecedented scale at room temperature in scalable materials, but also it can be controlled by very weak proximity effect. And using a lot of different type of van der Waals heterostructures, we can achieve very interesting active spin device. This is a theoretical work, which was one of the first to demonstrate that graphene can become magnetic when you deposit it on a magnetic insulator, such as YIG, in which the exchange coupling for a super clean interface was predicted to be gigantic. And as a result, very sizable band gap could be open and spin splitting of the band structure. Just a couple of days, or let's say a week ago, Bava and this group have evidence that you can use graphene interface with two-dimensional antiferromagnets, and that you can probe this type of proximity, giant proximity effect. And in their work, where they measure modification of the Hanley spin position signal, they could estimate that the achieved exchange coupling was in the order of 170 Tesla. So we have a lot of possibilities in order to design this type of van der Waals heterostructure with a functionality for spintronic. And but what I want to point out is the perspective for spintronic application in the field of non-volatile memory. Early on, the group of Chef in Grenoble, together with colleagues at CNRS, demonstrated that when you coat magnetic materials with graphene, you have a very important gain beyond preserving the property of the interface, avoiding oxidation. You will also increase considerably the PMA, the perpendicular magnetic anisotropy. And this is an important figure of merit for STT-MRAM technologies. More recently, together with a more international consortium, including a big company like Samsung or Global Foundries, we have set up a new roadmap for the next 10 years to come, in which we discuss all the aspects that current technology are facing with that could be solved by a proper integration of two-dimensional materials. And this in the perspective of STT-MRAM, but also spin-orbit torque-based non-volatile memories. So let me come closer to a more concrete illustration and discussion about the gain of this type of materials and heterostructure for designing active spintronic devices. And I will mainly point out the generation of pure spin current through the spin Hall effect, and its relation to the spin-orbit torque mechanism. So spin-Hall effect, as I am sure everybody knows in this audience, is the possibility to create pure spin current by an electric current when you use a strong spin-orbit coupling materials. Especially in this van der Waals heterostructure, one of the first interesting case was to enhance spin-orbit coupling in graphene, for instance, by depositing this transition metallic chalcogenide in order to locally separate the spin population and having this transversal spin current. So one question was, what could be the figure of merit of this mechanism? And in order to measure that, usually we use this spin-Hall current, which somehow tells you how much spin currents you can create for a given charge current. So there is a very important aspect here, because all conventional materials, let's say that the ones that have been reviewed here, and especially heavy metals, have been facing a lot of problems in order to respond to the demand of spintronic application. And the problem is the following, that usually you would like to optimize both the spin diffusion lengths and the capability you have to modulate the spin during the propagation. And the propagation can be very efficient, very long, but at the same moment, locally, you want to rotate the spin and make some kind of device, spin valves, and so on and so forth. But usually when you increase the spin orbit coupling in this type of materials, you might find the augmentation of the spin-Hall angle, but generally you also reduce the spin lifetime and the spin diffusion length, and vice versa. So that makes this type of material, so if you look at the correspondence, what you would like to achieve is really to come in this upper right part of the graph, where you maximize both of them. And one important point here is to keep in mind the fact that with these conventional materials, the product of spin lifetime times the spin-Hall current is in the order of 0.1 nanometers. So the absolute value of this product doesn't mean really anything. What is important is that maximizing both quantity means to enhance this number. So one of the questions we addressed and we answered was how this type of interfacing could indeed bring an enhancement of spin properties and overcome the limitation of the previous materials and the previous rule I've just mentioned before. So to investigate this, we first studied theoretically the capability of this type of interfaces to generate large spin-Hall currents. We are very lucky in the sense that when you interface graphene with a lot of different materials, as we have reviewed now in the paper here, you can have a very realistic description of the impact of this proximity effect, not only on the bond structure, but also on the spin texture of the state. And the spin texture of the states will be fundamental to understand the resulting spin transport properties. So we have, in addition, based on a lot of calculation from first principle, realized that you can have a minimum set of effective Hamiltonian that will capture all the possible type of interfacing you're interested with, especially including these new 2D magnets or the strong spin orbit coupling materials. So then, based on this description of this effective Hamiltonian, we can investigate, compute exactly the spin-Hall angle, for instance, using this ratio of the spin-Hall conductivity over the dissipative conductivity. So to explore the property of complex interfaces, and especially if we want to deal with also the defect, we had to recourse methods that are said to be linear scaling, and to scale linearly with the complexity, with the number of atoms of the system. So using this type of methods, we are able to compute for given interfaces these type of quantities, and to evaluate the figure of merit for the formation of pure spin currents. This is what we did, and we found, for instance, in the case, this is an illustration for the case of intrinsic spin-Hall effect, when you are just related to the bond structure, the modification of the spin texture, that we found we could predict that, for instance, tungsten disulfide should lead to a larger spin-Hall angle. And in presence of disorder, we also found that spin-Hall angle could reach several %, provided that the interface quality will be enough. So first experimental results, which have been very promising, was reported by the group of Felix Casanova and Rusueso, where they observed up to room temperature some signal that could be assigned to the spin-Hall effect. And they have also investigated this as a function of temperature, and basically could find the evolution of the spin-Hall angle as a function of temperature. The point here is that, unfortunately, in this device configuration, there was no possibility to tune by a gate the position of the Fermi level, so we cannot really be sure the possibility to improve this by gating. And gating is also very important in order to design an active spin device. This was realized shortly after by the group of Sergio Valenzuela, in which an ambiguous signature of the spin-Hall effect was reported, and in addition, a gate dependence of the spin-Hall angle could be evaluated. And in this case, this measure were done up to room temperature. The conclusion about the figure of merit for graphene deposited on transition metallic chalcogenide was that the product of the spin diffusion length times the spin-Hall angle could reach at least 2 orders of magnitude higher than a conventional metal like heavy metals. So that's a very good achievement on a system at room temperature, on a system that is scalable. More recently, people have found that transition metallic chalcogenide could offer some new value for spintronics. And in particular, this material like molybdenum ditelluride or tungsten ditelluride were investigated, and interestingly, as you see here, in different work, they found sizable products of the spin lifetime, of the spin diffusion length times the spin-Hall angle, but yet in the order of this interface. Another result on multi-layer of molybdenum ditelluride conclude on spin-Hall angle of 30%, like again, very high, with a spin diffusion length of 1 micron at room temperature, while the product will reach 300 nanometers. So here we are speaking about 5 orders of magnitudes larger than what we know for conventional heavy metals. However, this work and the interpretation is debated. So that was very interesting from a theoretical point of view to try to understand what happened in this type of materials, which we can very well described also using first principle simulation. And this kind of calculation, this is an example for bond structure of monolayer, molybdenum ditelluride or tungsten ditelluride. One very interesting information is the fact that if we look at the spin texture nearby these bonds, we find that there is a so-called persistent canted spin texture, which is a very interesting aspect that has not been seen in other kind of heavy metals, or even for graphene on top of TMDs. The spin texture is very different. So persistent spin texture means that it is kind of K-independent in the zone of interest for transport. And we'll see that these counted angles actually reflects in all the property of the spin transport. So we can elaborate effective model again in these materials, and we can describe by, for instance, using type binding model and look at symmetries, and we can reproduce quite reasonably the main features of the bonds and of the spin texture. And by doing that, what we could do is first of all to investigate the spin dynamics in the system, and indeed confirm the emergence of a strong anisotropic spin relaxation. And here you see the non-local resistance as a function of the channel length for this type of device configuration, non-local geometry, where you inject a current between a magnet and the contact here, and you measure far away from the current flow a non-local signal. And you clearly see the difference that your non-local resistance is much difference between the Y polarization of the spin injected, the Z and the X. And this is fully consistent with the strength of the spin orbit coupling parameters. And so that reflects this modification of the spin diffusion length. Okay. We also study the evolution of the spin lifetime in spin diffusion length as a function of the energy, and find that there is a tendency to increase when you get closer to this bound edge. So we could make a very complete analysis of this phenomena and related this modification, this anisotropic property, spin transport property, based on the spin texture. And basically, we could also evaluate the spinel angle using two different approaches. One which is more like brute force bulk simulation using the Kubo-Bastin calculation that we show here, and another one which is using the non-local transport simulation, so that you can really evaluate the spin accumulation at the boundaries, and from that you can also extract, using fitting to a spin drift diffusion equation, you can extract the spinel angle. And both results agree very well. And as a result, most important is a figure of merit that we found for this type of materials is the order between 10 and 15 nanometers. So indeed, these materials, we don't reach 300 nanometers as the extraction from one paper was claiming, but definitely we are going to order of magnitudes that are extremely high, and so show that this new type of materials could present a high value in the context of spin transport devices. Finally, I'd like to point out that these materials can also manifest a full band gap, and in this condition, then it is possible to observe even a quantum spinel effect. Okay. So this was reported in this paper in 2018, the group of Jarrillo Herrero in MIT. However, these are pure electrical measurements, so there has been no visualization that this type of quantization do correspond to a very peculiar spin texture of the possible boundary state. So we did this type of calculation here. It's a lot of equations, and there is not the reference to the paper, which was published in Physical Review Letters. But basically, we could confirm that indeed the onset of quantum spinel effect, the possibility to open to visualize boundary states which are topologically protected, is related to the specific bound structure and the lowering of the symmetry of these materials. And we could make the simulation and get a confirmation of the quantization of the spinel conductivity as a result of this counted spinel angle. And by simulating non-local transport, we could also confirm the appearance of this plateau in the non-local resistance with a full relation with boundary states which are purely polarized in the counted spin direction related to the spin texture of the state. Okay, so that showed that there is quite a lot of richness in all these materials, and that there are many rooms to improve the capability of such materials to generate spin current and also to control and manipulate the spin currents. Just mentioned that what I've just shown about the counted spin Hall effect has been confirmed experimentally by this group. Let me finish to discuss the point that we have a lot of interesting degrees of freedom in this van der Waals heterostructure. Indeed, a lot of calculation, especially the DFT, have been made assuming most stable interface. But as we have seen with all the physics of the moire that has been emerging in the recent years, you have these degrees of freedom of twisting materials, especially these van der Waals materials. And so you have a lot of possibilities to manipulate further the parameters, the symmetries and the spin orbit coupling parameters related to this material or the exchange coupling fields. So it turns out that there are possible ways to optimize the type of heterostructure you have to fabricate in order, for instance, to generate many different possible spin orbital components, and especially to achieve spin orbital components that will allow a switching of the magnetization of the materials of interest at zero magnetic field, so which is a kind of gray. So what I want to conclude with that is that we have still an enormous playground to investigate it, having in mind that we like to optimize the properties that will be then very useful in next generation of spintronic devices, especially the one I have mentioned before, related to STT-MRAM or SOT-MRAM. So let me just mention that part of the simulation that I've presented have been made using this linear scaling quantum transport methodology, which are essential in order to go realistic in the prediction, and that we have developed a platform in order to make the codes available and to engage partnerships with researchers and with companies. So this is the end of the talk, half an hour, as I was asked. Thanks for the attention. I'm sorry not to be there again. Looking at those photographs of Cefalù, sorry. It's kind of an unbelievable landscape and city. So I hope that everybody will enjoy the workshop anyhow. and that in a very short time we will really have the possibility to have all this meeting in person again, because of course we are lacking the opportunity to engage more discussion, having a special Italian dinner or Italian drinks and so on and so forth. So anyway, you are lucky to be in Cefalù, and enjoy it a lot. And if you have any question, I really invite you to contact me by email, and then we can have a kind of Zoom discussion about whatever you would be interested in. So thank you very much, and have a good workshop.